Let's take a look at the chain rule formula for derivatives. So in a previous calculus class, I expect you've seen the chain rule formula. This is how we calculate derivatives when we have functions composed together. So I'll have some function f of x, and the input to f of x is another function, which I'm calling g of x. This is a very common situation when we're working with functions. And since we are in the business of calculus, we like to study rates of change, and we'd like to know how to take a derivative of a function that looks like this. So d dx f of g of x. The formula you've probably seen before is that we're going to take f prime, so this is the derivative of f of x. Inside of f prime, we're going to place the function g of x. This is the original g of x. We have not performed a derivative here. To finish the formula, we multiply this expression by the derivative g prime. So the formula for this derivative is f prime of g of x times g prime of x. Okay, formulas are all well and good, but I find it most helpful to work with an example. So let me pick a function. I will be using the logarithm, and I guess here I'm using the base 10 logarithm. And inside here, I'm placing tangent of x. Let me go ahead and put those parentheses on there. So if this is the function I'm going to differentiate, then I need to identify what are the inside and outside functions. So here, I'm going to make notes for myself, and I will say that f of x is equal to the common log of x, or the base 10 log, if you prefer. My g of x is going to be the tangent function. And we can double check f with a g of x inside is exactly log of tangent. So that's all looking good. The next set of notes I need to write for myself are the derivatives of both of these functions by themselves. So first up, I need to find what is f prime of x, what is the derivative of the common log, or the base 10 log. And you might remember that the derivative of the natural log is 1 divided by x. And we can use that here. This derivative is going to be 1 divided by x, but since I'm using a different base logarithm, I also have a 1 divided by natural log of 10 here. That's my conversion factor. Just as a reminder, if I have any logarithm, say base 10, I can rewrite that in any other base using the formula like this. So to convert by bases, I just divide by the log of the old base. And that's why I have this conversion factor here. Okay. That is my f prime. I still need to calculate the derivative of g, the derivative of the tangent function. G prime of x, derivative of the tangent function, is, of course, secant squared of x. I like to think of these notes as the ingredients for my formula. So my recipe, if you will, is saying I need an f prime with a g of x inside and a g prime outside. So f prime, g of x inside, g prime of x outside, and I'm just going to copy these formulas from the notes that I already took. F prime says I need, oh, I'm almost out of space there. There we go. Let's just move to a new page. F prime says I need a 1 divided by the natural log of 10 and 1 divided by x. However, I need to replace that x with the formula for my function g, which is right here. It's my tangent function. So this will be 1 divided by tangent of x. All this stuff right here is my f prime of g of x. I need to multiply by g prime of x, like so. And I am using dots here because my x's are reserved for a variable. G prime is the derivative of tangent, which once again is secant squared of x. So the solution to this derivative problem is that the derivative of log base 10 applied to tangent of x is 1 divided by the natural log of 10, 1 divided by the tangent of x, times the secant squared of x. That's the answer. Now, as you become more familiar with taking derivatives, as you remember all of these tricks from previous calculus classes, you can get to a point where you can work a function from outside in. So let me take this same problem now, but working from outside in, I won't be writing those same notes to myself. So I look at this, I identify the outside function is my log base 10. My inside function is the tangent. When I go to take a derivative, there is my derivative symbol. This is going to be equal to the following. Step 1, take the derivative of the outside function. I know that this derivative is 1 divided by log 10, 1 divided by x. When I get to any x here, I need to substitute the inside function the same way that it appears previously. So here's my tangent of x. That's entirely the derivative of the outside function with the inside function inside of it. I still need to multiply by the derivative of the inside function, which again is secant squared of x. I get the same answer here, but all of the bookkeeping that I did on my previous page, I've now done inside my head. And it helped that I was saying this stuff out loud as well. Either of these methods are fine, and you can see that both of them get us to the same result. When you are coming back to school after maybe not thinking about calculus for a while, that's fine. I would recommend writing out the ingredients. When I am looking at my own scratch work, it's much easier for me to know what's going on with the different parts of the functions labeled, and also a note of what those corresponding derivatives to feed into the formula need to be. The benefit of writing out these notes for myself is that later on, if I have made a mistake, then it's easy to figure out, okay, well, maybe that's supposed to be secant squared. Where did I put my secant squared anywhere else? I can just change that to what it's supposed to be. It makes the algebraic work a lot easier to diagnose. So if I just looked at this, I'm thinking to myself, oh gosh, why is that the case? It might not be obvious that derivative of log base 10 is 1 divided by log of 10, 1 divided by x. So there is no shame in writing this stuff out. The secret that a lot of mathematicians use is we just don't publish our Scratch work. We do all this stuff the morning before, and we come into class remembering what to write on the blackboard. It makes you look a little smart, but the truth is we all do this stuff in the margins.